So good evening everyone. I hope you had time to go through this week's lecture. We'll be covering mostly graph algorithms which are related to finding shortest path between two nodes or all pair of nodes. So we'll look at some algorithms and some problems related to that. So have a look at this first question. Read it. It's actually quite a simple question, but it's just there's a lot of text in it. What will help is the graph that is described in the problem. If you are to draw it, then you'll get some clarity. So the problem is related to Dijkstra's algorithm and breadth first search. So first just draw this graph that is mentioned between cities and just read what a shortest path between city is. Hi Rahul, good evening. So start this problem by making a graph. I'm going to show you what the graph looks like, but it's important that you can convert a text into the proper graph. Put all the vertices and edges and just check if you have to basically calculate the shortest path between two cities, what that will look like, and will that answer be different if you use Dijkstra's algorithm versus BFS. If you solve the question, you can put your guesses in the chat box. Just the option. I've got only one answer so far in the chat. Do you guys need more time, or are you confused about any of the algorithms, Dijkstra's or BFS? Or are you not clear about the graph that will come out? Okay, we'll look at Dijkstra's. And BFS, I hope it's clear, because that will not go into. It is similar to DFS. It's just how you prioritize visiting nodes after one another. So if you are not clear about BFS, you should ask now. Otherwise, we'll look at how Dijkstra's algorithm work. Okay, so first let's look at just the graph of this algorithm. What will that be? So you have Bhopal in the center and you are given 4 cities around it. Now any city apart from these 5 cities, if you have to travel, you have to go via these cities. So like they have given an example. If you are traveling, let's say from Vellore, you have to send something, then you need to come to Chennai, then to Bhopal, and then you will go to the next city. But let's say if you have to put a courier from they have given as example Bhubaneswar, Kolkata to Patna. So Bhubaneswar, Patna connecting via Kolkata, so that you can send directly. Otherwise you have to go through Bhopal. So what would be the graph of this thing? So it will look something like this. So you have Bhopal at the center, then you have the 4 cities around it. The examples that are given in the question. So it's basically, if you want to send something from Pune to Vellore, then you go basically from Pune to Mumbai, then Bhopal, then to Chennai and Vellore. Now what the question is asking is, if you were to compute the minimum number or minimum, you can think about as distance, or you can think about the charges. So you have to basically compute a shortest path between 2 nodes. Now if you are using Dijkstra's algorithm or BFS, will the answers be different, is the question. So what is Dijkstra's algorithm exactly? For any given graph, Dijkstra's algorithm is used to compute distances between like basically shortest path between 2 given nodes. So you can apply it for any 2 given nodes, or you can even apply it for all pair of nodes in your graph. So for example, let's say we had to send something from Pune to Bhubaneswar here, okay, in this graph itself. So we start at Pune, which is our origin node here, and now we keep computing distances from Pune to its neighboring node. So Pune will only be connected to Mumbai. So if the distance of Pune, we start with 0, so and let's say all the edges have some weight, or you can just assume that it's 1. It really doesn't matter for this problem. So but you basically start from Pune, then you move to Mumbai and you add 1 there. So Mumbai would be basically a distance 1 away from Pune. Then you go to Bhopal, okay, because Mumbai is only connected to Bhopal, like for like the only member. So basically this would be a directed graph. So I haven't shown the edges here, so it will be basically Pune to Mumbai, then Mumbai to Bhopal. And then if the again edge weight is 1, so you will put 2 on Bhopal. So you're calculating basically distance of all the nodes from Pune. Okay, then you move to Kolkata, add another one, and then to Bhubaneswar. Then you'll get basically 4 in total. So that is your path length from Pune, Mumbai, Bhopal, Kolkata. It's an intuitive algorithm. The only thing is how it works is when we are at Bhopal, we are going to reach all the nodes that connect to Bhopal. Okay, and we are going to add 1. So we are going to add a 1 on Delhi, Kolkata and Chennai. Then we move to basically Kolkata, and then to Bhubaneswar and Patna if we had to calculate there. So Dijkstra's algorithm just works intuitively. You keep moving to the neighbors of your given node and keep adding the edge weight, whatever is given. Okay, so in this example, if you were to calculate charges or your shortest path, so the distance between Pune to Bhubaneswar would be 4. Now if you were to use breadth first search here, breadth first search would just be again looking at the neighbors, all the neighbors before going another level down. So you look at Pune, then Mumbai, then Bhopal, then you look to Delhi, Kolkata and Chennai. Okay, and then basically you go to Bhubaneswar, Patna, and then finally to Vellore. So the answer to this problem is because it's a so this is a spanning tree basically, or this is a tree structure here. So basically the graph doesn't have a cycle in it. There are no cycles present, and it's just a tree. So it wouldn't matter if you calculate with Dijkstra's or with PFS, you'll get the same amount of charges. So this wouldn't have been the case if you were given basically a graph which is not a tree, so which has cycles in them. So because in that case, Dijkstra's and BFS are going to give you, you're going to reach basically neighbors differently in both of these algorithms. So if this is not clear, you can ask right now, otherwise we'll move to the next question. Because it's a tree, there are only one path between any two given nodes. There wouldn't be multiple paths, and you're going to just reach that exact path through Dijkstra's or BFS. If it would have been a graph not tree, then you would have multiple paths, and then you can have multiple answers. So this is just true for this given graph because it's a tree. Okay, don't get confused. If it's not clear to you, you should ask. Otherwise, we'll move to the next question. Okay, so the next question. So you are not given any particular graph, but you are just given an abstraction of it. What you have to think about is if you were to add a fixed weight on each of the edges, then will your path finding algorithm change? Or will it give a different answer basically? So in this question you are given that let's say you have given number of cities and there can be shortest path between those cities via different cities. So now you have to think about if on each of the journeys you're going to add a fixed cost.
Sir, Smith, can I speak?
Yeah, man.
In my opinion, the answer should be B, because
Okay.
more sectors, yeah. Because uh, on each sector, the convenience fee of rupees 300 has been added on each sector,
Mm-hmm.
not on each flight. So passenger has to pay a little extra.
Yeah.
So TripGuru need to recompute the cheapest route when there is a longer route in terms of number of flights. In my opinion, answer should be B.
Okay. And so you should think about whether the answer should be B or C. Like with
Yeah, clearly.
so should it be B or C? Like would it favor more sectors or fewer
Okay,
sectors?
sorry. Cheapest route, है ना?
Yeah.
Recomputed cheapest route. The
Mm-hmm.
surcharge favors hopping flights with fewer sectors. No sir, surcharge favors hopping flights with more sectors, in my opinion. नहीं,
Okay.
favors word मेरे को clear नहीं है यहाँ पर.
Hmm.
From passengers perspective or from TripGuru perspective.
No, so like trip crew or passenger, they are both calculating basically the shortest path or the smallest charges that they can have
Then
on.
surcharge favors flights with fewer sectors. Option C should be correct, sir.
Yeah. Let others also try, and we are going to look at the answer. So a good way to solve these questions is just to make a sample graph kind of thing, like a very simplistic graph. Just make a graph with 3 nodes, okay, and just put arbitrary edge weights on this graph and just add 300 to it and just see like will the shortest path change or not. And remember here we have to find shortest path between any two pair in graph. So between any two pair of nodes we have to find the shortest path. So we have to just look for the fact that will the shortest path between any two chosen nodes, will that change or not. Okay, let's look at the solution. So we'll start with a very simple graph here. So let's say we have a node marked origin and we need to travel from this origin to destination. Okay, now there are two ways to do it. There's a direct flight, okay, that costs 5,200. Now there is another set of flights which go via another node, let's call it layover, and the two legs of the journey cost 2,000 or 3,000. So you can go from origin to destination via this path and take 5,200, or via the layover path, which will be combined 2,000 plus 3,000, which is 5,000. So in this case, what would be the cheaper option of the two? Out of these two options, going via layover or taking a direct flight, which would be the shortest path? You just have to see the edge weights, and you just need to compare if via layover is cheaper or via direct flight is cheaper. Yeah. And now if you add basically 300 to each of the legs here, okay, and now see which one is cheaper. Yeah, so direct will become cheaper in this case, and because we had to find shortest distances between any given pair of nodes, so we have to basically take care of the fact. Now if we are adding 300 to each of the edges, so there's an extra cost added if we are hopping basically. So here before, going from origin to layover to destination was cheaper, but now because we have added 300 to each of the edges, so each hop is going to cost us extra 300. So now it's better not to take a hop and to choose direct flight. So in this case the answer becomes that the surcharges will favor hopping flights with fewer sectors. So if we are going from as many few nodes as possible, and if the path is as direct as possible, that can be better. So it won't be better in all the cases. So here it was just a special case where the 300 on each of the edges is just crossing the cost of the direct thing. So but the question is only about the possibility, like will they need to change it. So it can happen that they will need to recompute the shortest path and basically favor the paths with as many few nodes in between. Okay, if it's not clear, ask right away. Okay, we'll move on to the next question. Okay, so this is almost the same question, just read it carefully. The only difference is, instead of computing minimum distances between all the pair of nodes in the graph, you have to compute minimum spanning tree, and you have to see if that minimum spanning tree is going to change if you have added again 300 on each of the edges. So it's the same question, make the same kind of graph that I showed you earlier, and then check if the minimum spanning tree is changing or not. Just take your time. If you got the last question, you should get this part. Just remember, we have to make a minimum spanning tree of the graph. We don't have to compute shortest distances again in all the pair, but from a given graph we have to compute a tree which has edges weight the minimum. So the total edge weight should be minimized in that. Convert the graph into a tree and minimize its weight. Yeah, so there is a WhatsApp group. You can check the link on the discussion forum. You will find like basically a post by me with the subject useful links, and you'll find the WhatsApp group. link there. This one.
सर MST कैसे बन रहा है ये समझ में नहीं आ रहा.
So what you have to do is what you are given here is that the IT company has already selected a subset of airlines routes. Okay, so what the IT company is doing is they have a given nodes, like given cities, and they have selected path between those cities that they are going to choose for the flight. Okay, and now the minimum spanning tree here would be basically set of paths such that you will find connection between any two pair of cities. So if you pick up two cities, you will definitely find a path that connects them. Okay, so if you are given a graph which would be the airline's whole network, okay, so it will have all the paths connecting different cities, and there will be multiple. So if you need to basically go from a city A to B, like we saw before, like origin to destination, you can have via layover or via direct flight. Okay, now basically the IT company has selected a subset of these paths. Okay, it hasn't selected the whole network, but it has selected subset of the paths such that it's a minimum spanning tree, meaning that if you basically disconnect any of the edges, the whole graph become disconnected. It's a tree. Okay, so now the question is, if you're going to add 300 on each of the edges as weight, will that minimum spanning tree change? Okay, so the minimum spanning tree, you just make it, we are going to use again the same graph as before, origin, destination and layover. Okay, now try to make a minimum spanning tree of that graph before addition of 3000 and make a minimum spanning tree after addition of 3000. So we had this graph, right? So you have this graph, so I want you to make a minimum spanning tree of this graph and a minimum spanning tree of this graph, and just check if these two graphs are same or different. Okay,
Okay, sir.
so minimum spanning tree is nothing but your subset of edges. Okay, so here basically you have 3 edges, so but you do not need all the 3 edges. You, for minimum spanning tree, you can basically get rid of one edge and you will still have path between any two pair of nodes. Okay, now the edges have to be selected such that you get the smallest total weight. Basically the total edge weight should be minimized. So like if you are selecting, let's say 2000 and 3000, these two edges, okay, and you are basically getting rid of this 5200, then your total edge weight would be 5000, like 2000 plus 3000. If you are basically disregarding this 2000 edge and you keep 5200 and 3000, then you have 8200 as your total edge weight, which will be more than before. So this is not the optimal solution. Okay, so okay, I got one guess here. Again, there's no impact. Okay, okay, see. Rahul, do you want to take a guess?
Yes, sir. I think the answer should be C again,
Okay,
because the IT company has to recompute the route, and
okay.
the what we have is when there is a layover,
Mm-hmm.
we can see that in the case of layover and in case of direct flight, if we add, the question boils down to this fact that the airline is adding a convenience fee of rupees 300 on each sector.
Yeah.
So when we consider this fact, it becomes clear that the IT company would want a shorter route, point one, and of course they would love to have those routes, only those routes. Now layover or direct doesn't matter, which has shorter route. Initially they had a set of routes, but now they need to come. The argument almost
Yeah,
is
I
the
get
same.
it.
We are
Yeah.
looking for shorter.
Yeah. Okay. Now the only difference between what we were computing before and what we are computing now is what we are computing before is the shortest path between origin and destination in the previous question. Okay. But now what we are computing is what would be the minimum edges that we need to keep in the graph such that your graph is still connected. Okay. So here you are right that it will again be profitable if they recompute their path, basically smallest path, and keep this origin to destination. Okay. But basically they have to keep so basically now we have to create a minimum spanning tree. Okay. So in this case we have to have a path between all the three nodes, so we cannot just disregard this layover and not have any path which connects this layover. Okay. So I'll just give you how the graph will look like now. Okay, so this is our before graph. Okay, and now as I said we have to create a minimum spanning tree, so which would be that we can basically check out one of the edges, okay, such that whatever the remaining edges are, their weight should be minimized, the total weight. Okay, so here what would be the minimum spanning tree? This would be the minimum spanning tree, because you have to basically still connect all the three nodes, but you want your total edge weight to be minimized. Okay, now if you were to keep this origin to destination edge weight, okay, so this will be 5200, and which will be more than checking out basically 2000 and 3000. So the IT company is going to keep this as their minimum spanning tree, like because they are still connecting all the three cities. Okay, and the total edge weight is 5000, which is the minimum value you can get. Okay, now you look at the transform graph. Okay, like we have 2000, 300, 300, 300 added on all the edges, and now think about what would be the minimum spanning tree of this graph with the given edge weights. Will it change or will it be same? You have to have two of the edges. You can disregard only one of them because you need to connect all the three nodes now. You are not finding the shortest path between origin and destination. You are finding set of edges which connects all of the three nodes. And
Sir, our
yeah.
MST would have destination as the root node of the tree and layover and origin as the other.
So minimum spanning tree is basically a set of edges. So you will have all the nodes as your original graph. So you have to have all the three nodes here, but you have to take a subset of all the edges that you had before. So we had three edges before, and now we are going to take a subset. We can disregard one of them and still keep all the three nodes connected. So now you tell me what you think should be the minimum spanning tree, if not what is shown on the screen.
It should be different. We have one edge that is 2500, other edge that is 3300, and the last edge that is 5500. So 2300, we have to just add 2300 plus 3300 boils down to 5600.
Yeah.
The other is 5600. We have two that are 5600 and 5601, and the other is 5800, and the other is also 8800. So
Yeah.
we will keep only 5600 and 5800. So that is we will have an edge between
minimize the total edge weight which you have in the tree. Basically, you'll have two edges, and you have to minimize the sum of these two edges.
The graph will be same, right?
Yeah, graph
in this case.
Yeah. So basically, you still get the same graph. You have now 2300 and 3300. Okay, and this edge that we have deleted is 5500. Okay, so because we had the constraint was to connect still all the three nodes. Just appreciate just the difference between this question and last question, because this confusion you need to get rid of. So the problem were different in both of the question. In the previous question, you were computing minimum distance between origin and destination. Here you are computing the Rahul, can you mute? Okay. Can you mute yourself? Yeah, thank you. So here basically the question is different, and it was regarding computing a subset of edges such that your total edge weight is minimized. Okay, because you need to connect all the three nodes in this. You are not just concerned about two given nodes. You're computing basically all the like paths between all the nodes. Okay, so your minimum spanning tree remains the same irrespective of the addition of 300 on each of the edges. So this is your answer, that there is no impact. Okay, if it is not clear to you, you should ask me right now. It's important to clarify like how should we tell if the problem is asking us to compute minimum distance between nodes, or is it asking us to compute a spanning tree. It's in the language only, and you just need to like read enough questions to get that language, like what they're exactly asking. Okay, I hope you don't get confused. Yeah.
So with just one clarification.
Yeah.
In minimum, when you are drawing a minimum spanning tree for a graph, so the graph will remain unchanged pre-incrementation and post-incrementation, right?
Yeah, if all the edges are incrementing by a fixed constant, like we are incrementing 300 to all. If we are incrementing variable amount, then of course we'll need to recompute it.
Yeah.
Okay, fine. Let's look at the next question. So it's actually about Prim's algorithm and Kruskal algorithm, and it's little tricky just to do it. So what I want you to do is basically solve this problem on again how we took a sample graph, like just 3 nodes, and I just want you to put basically either equal edge weights on it, or put unequal edge weights on it. Okay, and check how Prim's algorithm or Kruskal's algorithm, will they give you the same spanning trees or not. Okay, just again take this sample graph with 3 nodes, and just give them either equal edge weights or unequal, and see the difference. Do you guys remember Prim's or Kruskal's algorithm? Did you come across in the lectures? Okay, let's look at Prim's algorithm first. So what is Prim's algorithm? So it is basically, if you are given a given pair number of nodes, okay, and you need to compute a minimal spanning tree. Again, minimum spanning tree would be a subset of edges, okay, and the total edge weight should be minimized. So what the algorithm is, that you initialize from any given node, any node that you have here. So here we have taken this node, let's say. Now we are basically going to look at the edge, the next edge that we are going to incorporate in our spanning tree would be basically minimum distance out of all other given edges, okay, and it should basically grow the tree. So here basically we are connecting nodes after another such that they are connecting to the previous node which is already in the graph, okay. So you have a set of nodes which are already connected and a set of nodes which are not yet in the tree, okay. Now what node, the next node that you are going to add is basically which has the minimum edge amongst all the left edges, okay. So here basically you can see that you are given nodes in a 2D space, and this particular example shows you how to create a spanning tree based on the Euclidean distances. So what you are basically doing is whatever nodes are closest to this tree as it is growing, you are incorporating them in that order, okay. So whatever edges are closest next to this growing tree, okay, and you just keep repeating it until all the nodes are exhausted, okay. So this is in a nutshell, it's Prim's algorithm. So you're just growing your tree such that you're taking the minimum edge weights, okay. If this algorithm is not clear, you can ask, otherwise we'll move to Kruskal's algorithm. So you're just taking nodes which are closest and just growing the tree until all the nodes are exhausted. That is pretty much it, okay. In Kruskal's algorithm, what we do is instead of growing your tree one node at a time, we are basically taking the edges which are smallest out of all the remaining edges, okay, and we only take edges such that they connect to unconnected tree and not the edges that connect the same tree. See, all these edges we are ignoring because they are connecting the nodes which are already connected. So because the whole aim is to create a minimum spanning tree, so we do not need any cycles, okay, we do not need multiple paths between two given nodes, we just need one unique path. So we are going to ignore all the edges which are connecting the same tree, okay, and we are only taking the edges which are shortest and are connecting to unconnected trees, okay. So just look at how the animation plays out, how basically they are checking the shortest edges which are blue and they are incorporating it if they are connecting to disconnected trees, okay. Just look at it and tell me if it's not clear. Okay, so now with this information, like you have two ways basically of choosing your edges. Okay, with this Prim's algorithm, you keep growing the same spanning tree until all the nodes are exhausted, or you're picking edges which are smallest amongst all the edges. Okay, so given these two ways of creating minimum spanning tree, what I want you to do is create a minimum spanning tree of this given graph. So just choose any one node at randomly, which will be your origin node. So that is picked up in case of Prim's algorithm randomly, and in case of Kruskal's algorithm, you are going to pick basically an edge which has the minimum weight. So just tell me, if you were to run Prim's or Kruskal's algorithm on this graph, what would be your minimum spanning tree? Or would it be a unique spanning tree? And will the spanning trees made by these two algorithms, will they be equivalent?
Sir, they won't be unique, sir, because in Prims we can choose C as the starting point,
Okay.
and then we will have CA and then AB,
Okay.
because it moves towards minimum weight.
Yeah.
In Kruskal's algorithm, it will first sort. AB would be minimum,
Yeah.
AC next, and BC. So it will choose AB first and then AC.
And
So
do we get the same spanning tree?
yeah, in this case we are getting the same thing.
Yeah, you're right. So if we put Prim's algorithm, so as Rahul said, if we were to, let's say, choose C or B or A in either of the cases, the next we are going to move will either incorporate the edge AB or AC, okay, and will never come on this edge BC, and this will be our minimum spanning tree. For Kruskal's, we are definitely going to choose the edge AB, and then we are going to choose AC, and again we'll have the same spanning tree. Okay, now do the same exercise if your edge weights were equal, and tell me what spanning tree or trees do you get from Prim's and Kruskal's algorithm. So for Prim's algorithm, just choose a unique any node, and then proceed by incorporating edges. And in Kruskal's, just choose the minimum edge, and then select next minimum edge, and see what spanning trees you get.
Sir, in Prims we can see that we can have CA and CB as one. But in case of Kruskal's, in my opinion, it would depend on the representation. If we are using a adjacency list, and if in adjacency list our first node in the adjacency list, the array of the list is A, then it will choose A as the first, because every weight is same. So the MST would be ABAC. But in case of Kruskal's, it will be it can be anything actually. In case of Kruskal's, it can be either CACB or CAAB. So in case of Kruskal's, I can see that yes, it will begin from A if we have something like that. But in case of C, as Harshit has just answered, we can have any of the two, either CACB or CAAB.
Okay. Why do you think in Prim's it will only be ABBC?
No.
Or
what I'm saying is one is option is I'm starting from C. I can start from anything. So in my opinion, it will have 1, 2, 3. Sorry, 1, 2. No. 2 minus 2 plus 6. It can have at least 4, in my opinion, 4 variations, depending on starting point.
Just think about, it will
That
help you
depends
to
on-
actually draw these spanning trees. Just see how many
Yes,
different
sir.
spanning trees you can draw.
Okay, I drew it on paper.
There is a chance that the answer can be same also for prims and crystals.
Yeah, but what are all the possible trees that you can make with each of the algorithm? Like Harshit and Ria, they are saying that crystals can have different spanning trees, but prims cannot. Yeah. Prim can also have different variation as crystals. So basically in prims, if you look, it's all about what is the starting node that we are choosing. Okay, so let's say if we choose A as the starting node, then we just go to B. Okay, and or let's say in this case this will come out if we choose, like, let's say B as the starting node, then we are going to basically pick BA. We can as well pick BC here, because there is variation on choosing the starting node and also what edges you are selecting, because all the edge weights are basically same. So if as you said, if there's an adjacency list, or depending on your data structure, or if you are just actually picking the same edge weights randomly, then it just depends on what edge weights you're going to pick. So either due to a different node that we are choosing in the beginning, or just because we are picking edges randomly, you can have all the 3 variations here, okay, in prims. And now in crystals also the case is same, because all the edges are equal weight, and the algorithm has to start by picking up the minimum edge. Now the minimum edge is same, 1, and for all the 3 edges, so you can pick basically any of the edge and grow the spanning tree, and again you'll have all the 3 variation. So if you look back to the question now, okay, so we were given a graph G, and these 2 algorithms give spanning tree TP and TG, and now the question is which of the following is true. Okay, so TP must be identical to TG. Do you think this is true? Yeah, as we saw that if the edge, so if basically you had different edge weights, okay, then it would have been true. You have 1, 2 and 3, so you are definitely going to get the same minimum spanning tree if your edge weights are different. But we saw if the edge weights are similar, then there can be multiple possibilities, and your algorithm might not output same spanning tree. Okay, so the first statement at least is not true. What about the second one? If TP is different from TG, some pair of edges in G have the same weight. Does this seem right, or does it seem wrong? If you have different spanning tree coming out of both the algorithm.
Partially correct. It's completely correct.
Okay, why is it not completely correct?
Because there is also a chance for same weighted edges, you might have TP equal to TG.
Yeah.
If you start from the same edge.
Yeah. But if they are different,
So they could be completely different, and they can't. It's like partially or completely different anyway.
so are you saying if they are completely different, then can you say that some pair of edges have the same weight? Like it's given that they are different. So if it's given that they are different, then it is definitely this case, and not the case where edges have different weights, because then we would have gotten the same tree. But if we are given that it is different, then do you think that some pairs at least should have same weight?
sir, in my opinion, if TP is different from TG, then all pair of edges in G should have the same weight. If the condition is necessary and sufficient.
So the condition is basically it's not necessary to have all of the edges as same weight. So here, like if you'll do this exercise again and make 1, 1 and 2 here, okay, and try the same exercise and see what you get, and then revisit this option. So just keep 2 of the edges as same weight and see if you're getting a different result. Okay, so option C is if E is a minimum cost edge in G, E belongs to both TP and TG. So here we saw if our case is that all of the edges are same 1, 1, 1, okay, then your minimum edge can be anything. Okay, so let's say your minimum edge EBC, it's a minimum edge, and so is AB and AC. All 3 of them are the minimum edges. So if this is given to you, is it true that it would belong to both TP and TG? Do we see that? Let's say BC is your edge in question, which is one of the minimum edge. So is it necessary that this edge would be the resultant edge in spanning trees given by both prims and cruscals?
Sir, it could be if we are taking minimum cases, then we can take 1 and 1, and then it could be similar.
Yeah.
If we are considering the minimum cases.
Yeah.
Because minimum में there are very less opportunities.
But it's just not a necessary condition, right? Because
Yes, sir.
yeah. So this option will be false. And if E is a maximum cost edge, E belongs to neither TP nor TG. Again, you take BC as the maximum edge because all 3 are the maximum edges. And it's given that it wouldn't belong to either TP or TG, which is not true. You can have a minimum spanning tree like ABC here, which will have basically B and C. So the option that is correct here is your B option, because if TP is different from TG, you have to have at least some edges that have same weight. As soon as all the edges are different weight, you're going to get a unique minimum spanning tree, and that will be the same respective of your using Prim's or Kruskal's algorithm. Okay, so if you're getting different spanning trees from Prim's and Kruskal's, that means some of the edges at least are equal. Okay, I hope this was
B seems to be correct, but when we consider C, if E is a minimum cost edge in G, when every cost edge is same, then any of them can be considered as a minimum cost edge, right?
Yeah, that is the point, and that is why, and basically any of your edge can be considered as a minimum cost edge, and it is saying that it will definitely belong to both TP and TG. So here basically
it will not. Yes.
Yeah, it will not. And same is true for maximum. You cannot guarantee that it would be neither in TP or TG. It can be, it cannot be. Depends on if you have equal weights or not in your graph. Okay, so just do this exercise, look at both of these algorithms actually, and try on maybe bigger graphs and more variations and see how they work out. Yeah. You can even find pseudo codes or like actual full-fledged codes, libraries containing these programs, and you can given and just online you can find like all these applications that will you put your graphs in it and it will give you the minimum spanning trees, and you can play around and see how these algorithms actually work. Yeah. Okay, last question and we'll stop the session. We're already running out of time. So this is about Bellman-Ford algorithm. Okay, and Bellman-Ford algorithm is basically it works kind of like Dijkstra's algorithm, but the difference between both of these is the number of times we visit each of the nodes. Okay, and Bellman-Ford was created such that we can find minimum distances between pair of nodes even when the graph has negative weights. So diastras can only be used if you have directed graphs with positive weights on each of the edges. So edges cannot have negative weights. But Bellman-Ford was specifically created so that we can handle negative edges. So just with whatever knowledge you have about Bellman-Ford, try this question, and then I'll explain you what Bellman-Ford algorithm actually is and what will be the solution of this question. But I want you to just try it for yourself first.
Sir, in my opinion, the answer should be B. The answer is the graph has a negative cycle.
So
Because
it is asking which
Bellman-
of the following is not a valid conclusion also. Like, be careful in that. So what the question is asking is which of the following is not a valid conclusion. So if you think that this statement or this option can happen, it's good. If you think that this option might not happen all the time, then that would be your answer.
Sir, as far as I understand, when a graph has a negative cycle, then Bellman-Ford algorithm does not work.
That is true.
Option B should be the incorrect. It is not a valid conclusion. But I'm not sure about if we iterate further, distances will continue to decrease. A and D are definitely correct conclusion.
So what you are given in the question is that you have run the Bellman-Ford algorithm already on n vertices, so you are done with n iterations basically, and now running it once more, like on the n plus 1th iteration, what you are observing is your distances are still decreasing, like your distances are not constant now. Okay, so if your distances are decreasing even after n iteration, then that already means that Bellman-Ford algorithm, it's not working. So Rahul, what you said that if the graph has a negative cycle, Bellman doesn't work, that is true. But if your distances are decreasing even after an iteration, then it already means it's not working.
Yes.
Yeah.
Then answer C should be correct. If we iterate further, distances will continue to decrease.
Is that a correct option or an incorrect option?
I'm thinking it has negative edge weight. That is true. So shortest path entry in iteration and plus 1 must be negative.
Okay, so let's look briefly at Bellman-Ford algorithm. I'll just show you an animation of it. Just couple of iterations. So basically you're given okay, so you're given basically one graph here and you need to compute. So A is your source. Let's say you will start your algorithm from here, okay, and you need to compute basically distances of all these nodes from A, okay, and you need to basically reach till F. So A is your origin and F is your destination, and you need to find what would be the shortest path towards from A to F, and what would be that what would be basically the length of the path, and what would be that exact path, like through which nodes will it go. So what we do in Bellman-Ford is we basically keep iterating on the nodes. Okay, so if you'll see how we have basically started this algorithm is we have this given graph. You can notice there are negative edges in the graph. There's -2, -1 here. So we start by so you see all the nodes listed here, A, B, C, D, E and F, and we start the distance of A as 0 because that is our origin node, okay, and we give infinity as distances to all the rest of the nodes. So this is the same thing done in the extras also, okay. Now what would be the first iteration of this algorithm? So we iterate over nodes. So first node that we are going to look at is A, okay. So when we come to A, we are basically going to look at the edges so basically just wait a minute. So we are going to basically look at the edges that come out of A, okay, and what would be these edges? So these would be this A to B and A to D, so 7 and 2. So once we have come to these edges, from B was assigned an infinity before, so from infinity we are going to assign it 7 because A was 0, so 0 plus 7 would be 7, and again 0 plus 2 we will assign 2 to D, okay. So this is first iteration and first node. We have just gone over A, okay. Now we are still in the first iteration. Now we are going to go on the next node, which is, let's say, B here, okay. So the algorithm proceeds and we go to B. Now B has only one edge that goes to D here, okay, only this edge. Now if we take this edge in account, so the distance of D, it becomes A to B and then B to D. 7 minus 2, 5. Now this 5 is more than what we had already listed for D, which was 2, so we are not going to take this into account. So the intuition behind this, the shortest distance from A to D will be this direct edge A to D, which is only of length 2, okay. And if we would have gone from A to B to D, we would have gotten the total edge weight as 5, okay. So we are not going to replace that now. So this is just B, and we just keep on iterating over each of these nodes. So the next node that we are going to be looking at would be C here, okay. Now C, if you will see, it has basically 3 of these edges which are coming out of it, okay, and C itself has a weight of infinity on it, okay. We do not have a path that goes to C till now in this first iteration, okay. So we are not going to change anything. These edges are not useful for us. We are going to just infinity from infinity to B, from infinity to F, so that will just give us infinity, so nothing is going to change here, okay. So in a similar fashion, we are going to just keep iterating over nodes one by one till we get a condition such that none of our weights are changing here, okay. So as we keep going on each of the edges, if we have come on a saturation such that our distances are not decreasing further, then that would be our optimal solution. What will be the case when your distances would actually be decreasing as you're iterating further? So here we have basically 6 nodes. We are going to have 6 iteration that we'll do, okay. And basically here in iteration 3 itself, we are going to find out that your distances do not change any longer, okay. So if the distances are not changing, that means that you have come on an optimal solution. You do not need to iterate anymore. In the worst case, you might need to iterate over 6 times, and in each iteration you are going over each of these nodes and all the edges, and you have to do it 6 times for 6 nodes. Even after doing it 6 times, when you're doing it 7th time, you see that the distances are actually decreasing. That means that there must be a negative cycle here. So let's say here D, E and C, like C, D, E, this triangle that you see, if it had like -3 and -2 instead of 3 and 2, okay, then every step that you're running this algorithm, you're going to keep finding. So if you go over and over on this path D, E, C, D, E, C again and again, if you're rounding, your path lengths are decreasing because the total cycle edge weight is negative. So it's actually beneficial for you if you are actually repeating over it again and again. So as you're iterating over it and your distances are increasing, that means that there is a negative cycle in the graph, and that's why Bellman-Ford is not working. Bellman-Ford works as long as there are negative edges in the graph but no negative cycles. So just remember this point. So then So the options were the graph has a negative edge weight. That is true. It must have. If the distances are decreasing, that implies that there must be a negative edge weight which is decreasing it. The graph has a negative cycle. It must be true because iterations, even after an iteration, we didn't converge on a solution. If you iterate further, distances will continue to decrease. That is true. If you have a negative cycle, the more iterations you do, the lesser distances you're going to get, and they'll become negative soon. And the fourth option, some shortest path entry in iteration n+1 must be negative. So the distances are decreasing, but it isn't sure that the values that we have put are negative. It can happen that they are not negative, because if you have a very big positive edge, so like 100 or something in our previous example, and you're decreasing it just with -1 or -2, so it will take a lot of iteration for it to decrease to 0 and to go to negative. So it might not be true that on n+1 iteration you'll have a negative shortest path. It might happen, it might not happen. With given enough number of iteration, like a huge number of iteration, it is definitely true that you're going to get negative paths. Okay, fine. So these are all the questions that we have for this session. If you're not clear with any of the question, I'll put the slides in recording as usual. You'll go through them and try these questions on your own, some dummy graphs, so you'll get better hang of it. And in case you have any doubt, you know how to reach me. People who do not have the WhatsApp group, I'm again telling you, just go on the discussion forum, and you're going to find the links there. Okay, and otherwise you can basically just put a post on the discussion forum and someone will share it with you. Okay, I just want to make an announcement that our next class is going to be on Sunday instead of Tuesday. So I'll be traveling next week, so I won't be able to basically take the class on Tuesday. We are going to prepone it, so we are going to have it on Sunday instead, the same time at 6 to 7 on Sunday. Okay, and yeah, we are going to cover this week's lectures in them. Okay, it will be just 2 days before, but I hope you'll be able to catch up with the course material during that time. So just remember, I'll put it in the chat box also. It is Sunday 6 p.m. Okay, next class, and from the week after that we'll again have regular classes. So it's just from next week we are going to have it on Sunday. Okay, fine. I'm going to leave you guys with that, and if you have any queries, I'll just tell you. You can ask.
Thank you, Smith. Thank you.
Yeah, welcome. Okay, thank you guys. Have a good evening.
Thank you, sir.
Yeah.